Hello, hopefully everybody's doing good today. This is the first lesson in Unit 7. That means you survived Unit 6, or you just skipped all the way to Unit 7 and do any of Unit 6, in which case I'm very disappointed in your work ethic. I'm just kidding. Okay, welcome to Unit 7. This unit is going to be all about transformations and similarity. So transformations is like changing things, either moving them, rotating them, making them bigger, making them smaller, stuff like that. So this object is going to be all about shapes and making them bigger, smaller, moving around. Cool. Today's lesson specifically is going to be about scale factors and enlargements. I think that's how you spell enlargements and reductions. So we're going to make objects bigger. That's what an enlargement is. And smaller. That's what a reduction is. And we're going to do that by using something called a scale factor. We're just going to basically jump in. Scale factor, the definition of a scale factor is it's a calculation to tell you how much bigger or smaller something's gotten. The calculation is that you take the image length, so that would be the new image, and you divide it by the original length, which is just the original. I'll say this, so SF for scale factor equals the new over the old. That's how I'll generally discuss it. I might use old, I might use original. I usually jump back and forth in between the two. But it's always new image divided by original image. And that's how you get the scale factor, which I just use SF to describe scale factor. If your scale factor is greater than 1, that means you have a larger object. If your scale factor is less than 1, then you have a smaller object. Your scale factor is always positive. We shouldn't be getting negative scale factors. It just wouldn't make sense in our calculation. An example. Let's look at this question right here. So we have two triangles. We have the original triangle. We have the image triangle. So the original turned into the image somehow. By looking at these, I can clearly tell that it got bigger. Because it got bigger, the scale factor has to be greater than 1. That's what that says. Because it got larger. We can tell this actually got larger by looking at the side length. So I know, like, obviously just looking at it, it's larger. But to prove that it's larger, I need to look at the actual measurements. So for instance, if I went from A to C in the old image, it was 3. When I go from A to C in the new image, it's now 6, which is definitely larger. I mean, obviously you could just look and tell, but it's good to actually have measurements to prove if something's larger or smaller or the same. You might notice this notation a lot. So if you look at my corners, I have corner C over here and then corner C with a little apostrophe. I call that C prime. Okay, that's what that apostrophe means. I just call it prime. So this would be A prime. This would be B prime. That's how I describe the apostrophe. Beautiful. That just basically explains what we do. This scale factor is technically 2 because we doubled it. So if you look, my size length went from 3 to 6. That's doubled. That's a scale factor of 2. We'll talk more in a minute about how to calculate scale factors, but this would technically be 2. Beautiful. Looking at this, we have our original over here, this penguin, and then we have 3 different penguins. Some of them have gotten bigger, some of them have gotten smaller. We're going to just guess the scale factor. We're going to estimate it. And we're going to talk about, is it bigger than 1, less than 1? So if I look at the first penguin right here, from the original to this penguin, I got smaller. Because I got smaller, that means that my scale factor, my SF, must be less than 1. Right? Smaller means it goes to less than 1. If I look at the second penguin, From the original penguin to the second penguin, I would say I have gotten bigger. Because I've gotten bigger, that means the scale factor must be greater than 1. Right? Getting bigger means your scale factor is greater than 1. And if I look at my third penguin over here, and I compare these two penguins, I would actually say from there to there, it's the same. Now, if they're the same, that means it can't be greater than 1 because that'd be bigger. It can't be less than 1 because that'd be smaller. So that means my scale factor, if it's the same, actually equals 1. Pretty easy, right? Awesome. Down here, just step by step of what we just did. Right? We looked at the original, we checked the new one, and then we figured out if it was going to be greater than or less than. Beautiful. Let's do example 2. So we're going to look at these two pictures. It's a diamond or a kite, depending on how you want to look at it. And we're going to talk about, did it get larger? Did it get smaller? What's the scale factor going to be if we estimated it? And then what is the scale factor? So let's start off by just looking at these images and figuring out, did it get bigger or did it get smaller? I would say this image definitely got bigger. That means that my scale factor, my SF, will be a number greater than 1. Right? It has to be. To actually calculate this, so these next few steps is actually us calculating. What you want to do is you want to look at your diamond and find two sides that correspond, so they're the same side. On the original, if I pretend I went from A prime to B prime, that would be the same length as over here, A from B. See how those two side lengths correspond with each other, right? They're the same spot on the image. Now that I've found two lengths that are the same, like they're the same idea in the two images, I'm going to figure out how long each one of them is. So from A prime to B prime, that was 2 centimeters. The corresponding, or the other side that's the same, but on my new diagram, that's from A to B, and that is 6 centimeters. To actually calculate the scale factor, your scale factor equals your new side length divided by your old side length. So for us, our new length was 6 centimeters. Our old one was 2 centimeters. 6 divided by 2 is 3. That means my scale factor for this picture equals 3. Easy, right? Find two side lengths on the image that are the same side length. One's just now bigger or smaller. And then do the new length divided by the old length. We got two examples here. We're going to try to calculate the scale factors. So we're going to zoom in on this triangle here. To calculate a scale factor, the first thing I want to do is find two side lengths that are the same corresponding side lengths. So on this little triangle, I'm going to go from here to here. That is 2 blocks long. On my new image, or my scale diagram, that would be the corresponding length. The same length, except now it's on the new triangle. And when I counted, it's 1, 2, 3, 4, 5, 6, 7, 8 boxes long. To calculate the scale factor equals new divided by old. In this case, the new is 8, the old was 2. This is a scale factor of 4. Awesome. If I look at these pictures over here, basically a boat. If I want to figure out if it's gotten bigger or smaller or whatever the scale factor is, I need to look at the original and find a side on the original that I can measure. I can measure the bottom of this boat. The bottom of this boat It goes from here to here. It's 1, 2, 3, 4, 5, 6 boxes long. I then want to look at the new picture and I want to measure the boat, the same spot, the bottom of the boat. If I measure the bottom of the boat from here, it would be 1, 2, 3, 4 and a half. So it's 4.5. If you get decimals, it might be smart to find lengths that don't have decimals. Okay, so when I do the bottom, like it looks like it's going to be 4.5, but I don't know if it's exactly 4.5. So measuring the bottom of the boat might not be the best choice. That means I'm going to look back at my original and I'm going to try to find another spot that I could measure. If I look at the top of the boat from here all the way to here, that measures as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 long. And if I look at the top of the boat from here to here, I notice I also get a decimal again, which isn't good. Right? I mean, it might work. It might be exactly 0.5, but we don't know if it's exactly 0.5. So I'm going to check another spot that I potentially could have done because I'm not really liking these decimal values. The next spot that I'm going to try is the flag of the boat. If I look at the top of the flag and the bottom of the flag on the original, it's 1, 2, 3, 4 across. If I look at the top of the boat here to the bottom of the boat here, now I don't have to estimate and use decimals. That's exactly 3. So when possible, try to find lengths that don't have decimal values. Just because we don't want to have to be guessing if it's actually 4.5 or 4.6 or 4.4, right? We would rather have exact spots like my green ones here on the top of the flag of the boat. Now, to calculate the scale factor, it's the new length divided by the old length. My new length is 3. My old length is 4. If I put that in my calculator, it's 0.75. So my scale factor equals 0.75. Just for fun, we could do the blue and the red lengths as well to see if they're the same. So if I look at the red, the scale factor would have equaled new, which is 4.5, divided by old, which is 6. And if you put that in your calculator, 4.5 divided by 6, you get 0.75. If you do the blue one, scale factor would be the new, which our new was 1, 2, 3, 4, 5, 6, 7.5. Our old was 10. That's 0.75 as well. So you'll see that every single length should have the same scale factor. I just don't like doing the decimal ones because they're usually not as easy to work with. I'd rather find the green one where it's whole numbers only. Awesome. We're going to look at more similar figures. So similar figures are like the same shape. It is important to note that in polygons, like these things that we had up here, different shapes, that's what a polygon is, shape, that the lengths are changing, but the angles that create the shape don't change. If the angles start changing, then the shape itself won't look the exact same. So it is important just to recognize in these polygons above that the angles aren't changing. Other thing you might want to know is the word congruent. Congruent means similar or same shape. You'll hear me use the word congruent every once in a while. Typically, when we talk about triangles, we talk about congruent triangles. That means like the same triangle. Awesome. Let's look at some pictures. So we actually do use enlargements all the time. Usually we have machines that do them for us, so we can do like an enlargement or a reduction on text when we photocopy things. That's a big thing that we see, right? I have a picture. I want to blow that picture up for whatever reason. I want to make it bigger. So I need to go to Staples, and I need to ask them, hey, could you make this picture this big? And what they'll do is they'll figure out the scale factor that you want, and they'll turn that scale factor into a percentage. If you wanted the exact same thing, so for instance, say you want a picture of this dancing cat or tiger or whatever the heck it is, and you wanted to copy the exact same. So you go to Staples, you're like, hey, I want this exact same picture. I want like 10 of them. Then the scale factor they would use, that'd be a scale factor of 1. They often don't use scale factors, they use percentages. To turn that into a percent, they then just times that by 100, and that tells them the percentage that they need to print at. In this case, 100%. This tells us that a scale factor of 1 equals 100% when I'm talking about things as percentages. If I look at this second one right here, that's an image that's been set to 200%. If I want to figure out what the scale factor is, then I just take the percentage and I divide it by 100%. And that gives me a scale factor of 2. Awesome. If we look over here, they give me a image. They want a reduction, so they want to make the picture smaller. I go there, I say, hey, I want this picture to be half the size. Then they would use a copy of 50%. If I want to turn that into a scale factor, that means I take my 50%. I divide out the 100% to turn it back into a scale factor, and it would be 0.5. Awesome. That's how scale factors kind of do apply to real life. We just usually talk about them as percentages in real life. We say we want something at 200%, 500%, 1,000%. We want something at 50%, something like that. We got a couple examples. Oh, one example left, and we're done. I want you to pause, actually. Now that we've done everything, so there's nothing left to learn today. So I want you to pause. I want you to try this question. Then I want you to unpause and see if you got it right. Okay, hopefully you did that. Hopefully you paused from that moment that I gave you, and you've unpaused and you have the answer. If I want to determine the scale factor, I'm going to remember that scale factor equals the new divided by the old. I need to find two spots on the original, and make a side out of that. Then I need to figure where that same side would now be on my new image. That same side would be over here on my new image. I then can put my new divided by my old. So my new length is 4 divided by my old length, which is 2. Put that in my calculator. It's a scale factor of 2. Perfect. If we wanted to do it backwards, so imagine that this was actually the original, and this was actually the image. Then my sides have now changed. So my scale factor would be new over old. But now my new image is 2 and my old image is 4. Because I've reversed the order of the image, that's now 0.5. So if I was to reverse it, it would have been 0.5. Beautiful. What we learned today, we learned that enlargements mean bigger. So an image is getting bigger. We learned that reductions means smaller. The image is getting smaller. We also learned that scale factors is how we describe things. If an image is getting bigger, the scale factor is greater than 1. So scale factor greater than 1 is bigger. We also learned that if you want to get smaller, a reduction, your scale factor is less than 1. So scale factor less than 1 is smaller. I hope you had an exciting, fun time doing this math with me today. Take care.